Everybody, this is example number 4 for structural analysis of deflections using the conjugate beam method. The problem statement that we have is we're asked to calculate the slope at support A and the deflection at the midpoint, point C, for the simply supported beam using the conjugate beam method. And EI, Young's modulus, times moment of inertia is constant. So here's our simply supported beam. And so the total length is equal to 6 meters plus 6 meters. That's 12 meters. And we have two concentrated loads. Each are at a quarter length away from the support. So here's our 6 kilonewton load here, which is 3 meters away from support A. And then we have our second concentrated load, also 6 kilonewtons. And this is also 3 meters away from support B. And so in this problem, we'll use variables. So like for load, we'll use P. For the concentrated load, we'll use P. And for the length, we'll use a variable L. And then at the end, we'll just plug in the numbers. And the midpoint is point C. The first step is we're going to determine the reactions at A and B at the supports. And it's pretty obvious just by looking at this beam that the reactions at A and B will be equal because this is a symmetrical loading scenario. So it's going to be equal to P, and this is also going to be equal to P. But I still went ahead and just went through the statics just so you guys can see. And I just wrote the two static equations, one for the vertical reaction, and then I took the moment about point B. And so it still comes out to be the same. The shear at A is equal to P, and then the shear at B is also equal to P. Next, we're going to construct a shear and M over EI diagram. So here's our shear diagram, and then our M over EI diagram. So it's the maximum value is going to be PL over 4 EI. After this, we're going to construct a conjugate beam. So the real beam, it's a pin support at A and a roller at B. And so the conjugate case, the support conditions will remain the same. In the conjugate scenario, the pin support remains a pin support, A prime, and the roller support remains a roller support, B prime. And here's our midpoint, C prime. And then we overlay the conjugate beam with the conjugate loading. And the conjugate loading is going to be the M over EI diagram. And the reason it's pointing away from the beam is the M over EI diagram, when you overlay it on the conjugate beam, it should always be pointing away from the beam. Okay. After this, we're going to calculate the slope at support A. So to calculate the slope at support A, we have to find the conjugate shear at support A. So we simplify the beam we just made with this conjugate beam. We simplify it by, instead of using this trapezoidal M over EI diagram, we just simplify and get a resultant. And so the resultant of the trapezoid is going to be equal to 1/2 times height times B1 plus B2. So that's going to be 1/2 times the height, PL over 4 EI, and then B1 and B2. We can just go back and see again. Here's our height of our trapezoid, and then B1 from here to here, we can say B1, and then B2 is equal to the complete length, and that's equal to L. So we have our resultant load, and because this is a symmetrical loading, it's going to act at the center. So to calculate the shear, the conjugate shear at support A, the most simple way to do that is just we take the moment about support B. So here's our static equation, and clockwise is negative and counterclockwise is positive. So we take the moment about support B, so negative VA prime, that's a shear, conjugate shear, times the moment arm L. And then our minus PL over 8EI times 3L over 2. And this whole thing is equal to the area of the trapezoid, area of M over EI trapezoid. So that's the resultant load, conjugate load. You can also write conjugate load resultant, conjugate load resultant. And the moment arm of this load is equal to L over 2, because from here to here, it's L over 2. And we just simplify it, and we get that the conjugate shear, which is equal to the real slope at A, is equal to -3 times P times L squared divided by 32 EI. And now we can plug in the actual numbers for the load and the length, and it comes out to be -81 kilonewtons times meter squared over EI. And now we're going to calculate the deflection at C. So here's our conjugate beam again. And so to calculate the deflection at C, we're going to take a cut at that location, and then we're going to calculate the internal bending moment, the bending moment of the beam at location C, the conjugate bending moment. So here's our cut. We have a conjugate shear and a conjugate bending moment, MC prime. And we also have the reaction at A, the shear at A, which we just calculated, 3PL squared over 32 EI, pointing downwards. And then we have this loading, this M over EI loading. And before we move on, well, we're going to look at this loading. We're just going to kind of divide it up to simplify it. So we have this triangle, and then we have a rectangle. So that's how we're going to divide up this loading. And to calculate MC prime, we'll just take the moment about point C. So here's the equation, 3P, and then counterclockwise is positive. So first we look at the shear, the reaction at A, 3PL squared over 32 EI times a moment arm of L over 2. So we have this covered, the shear at A, plus MC prime, and then minus, so like I said before, now we have to look at this loading. So first we're going to take a look at the triangle, this triangle here. Okay? So the triangle, the resultant of the triangle is going to be equal to base times height divided by 2. So 1/2 times the base is equal to L over 4, and then the height is equal to PL over 4 EI. PL over 4 EI. And then the resultant of this triangle will be acting at the third point, so it's going to be somewhere here, and so it's going to be here's the location for the resultant is going to be L over 4 and then times 1/3. So the moment arm of this resultant about point C will be equal to from here to here. So it's going to be equal to L over 4 plus L over 12. So we have all this now. So that's how we got this expression, 1/2 times L over 4 times PL over 4 EI. That's the resultant of the M over EI diagram for the triangular part. And then the moment arm is equal to L over 4 plus L over 12. And then minus, then we also have to take a look at the rectangular portion. So the rectangular portion, the resultant will be equal to base times you can say length times width. So the length is equal to L over 4, and the width is PL over 4 EI, and it acts in the center of this rectangle, and the distance from point C to the resultant is going to be equal to L over 4 divided by 2, so that's L over 8. Okay? And that's what we have over here. L over 4 times PL over 4 EI times L over 8. So now we just simplify this equation. So this is MC prime equals PL cubed over 96 EI plus PL cubed over 128 EI minus 3 times PL cubed over 64 EI. And so MC prime, which is a conjugate bending moment at location C, is equal to the real deflection at C. It comes out to be equal to negative 11 times PL cubed over 384 EI. And lastly, we can plug in the numbers for the load and the length, and we get negative 297 kilonewtons times meter cubed over EI. So this is the end of this example. Please subscribe to the channel. Check out the website. It's EngineeringExamples.net. And please like the Facebook page. It's facebook.com/engineeringexamples. And by the way, on the website, you can sign up for the weekly email newsletter, and this will let you know the new updates that are going on, the new content that we're adding. See you guys in the next video. Thanks.